Hi, this is William Trice. Today we're looking at an arc on the XY plane with constant charge density, and we will find a electric field vector equation for an electric field vector along the z-axis and show that for a completed arc, our electric field vector looks something like this. So here's our initial equation that we can use for the electric field vector, and then we can draw a diagram. And so from our diagram, we know that z is some distance z away, and that our arc has a radius of a from negative alpha to positive alpha with some change, which is negative alpha to positive alpha. And that gives us our r vector and our r prime vector. And then we can find our script r vector for our equation. And then using that, we can simplify it to z squared plus a squared because sine and cosine integrals are nasty. And then that gives us our general equation. However, we can take our general equation a couple steps farther by integrating from negative alpha to positive alpha. Then after our integration, we find the cosine component is always going to cancel, and that this is our general equation. It's going to be the k hat minus the I hat direction once we sum those up. However, at this point, I am going to solve this integrated general formula for our completed circle, which is from, or completed arc, which is from negative pi to positive pi, because that's the largest our arc can actually get, which is a complete circle. And then we get our equation, which looks just like our original one that we wanted to show that equals. From this, we can tell that as our radius gets bigger, the electric field vector magnitude on our point will get smaller, as well as when the point gets farther away, the electric field vector magnitude will get smaller. The difference between this and the general one is that this will have some, our general one will have some horizontal electric field pull on it. So it won't go straight up. For our general, for the completed circle, it will always push it up as long as our, well, always push it vertically, depending on whether our charge density is negative or positive.